Welcome back, Dragons. I'm still here taping for you on Friday evening. We're on page 24. Are they equivalent? I've added this page to help you with some things that we've been struggling with during our warm-ups. So what we're going to do is we're going to look at two expressions. This one over here and this one over here. We're going to determine if they are equivalent. We're going to determine that in three different ways. We're going to do a table where we're going to substitute some values. We're going to try to graph it using the values from the table. And then I'm going to show you a property proof, which we did in class together as a group. Okay, so take a moment. You might want to copy some of this down, pause the video, copy some of these expressions down, but I'm going to zoom in on the table now. So when determining if they're equivalent, you can take a value for x, because they both expressions contain an x, and substitute it and see if your answer comes out to be the same. We did this in a warm-up before. Let's try it out now. So I'm going to put a 0 everywhere there's an x. So 6 times 0, 6 times 0, so if we need to work this out, we can. So 6 times 0 plus 9 divided by 3 plus 4. 6 times 0 is 0. 0 plus 9 is 9. So then you're going to get 9 over 3. 9 over 3 is 9 divided by 3, which is 3. 3 plus 4 is 7. Now this one should be easier. If x is 0, this would be 0 plus 3.5, which is just 3.5. 3.5 times 2 is how much? 3.5 times 2. That's right, it's 7. So far, so good. But we're going to test a few more. Let's pretend x is worth 2. 6 times 2 is 12. 12 plus 9, 21. 21 divided by 3 is 7. 7 plus 4, 11. Very good. Now let's try this one. 2, if x was 2, 2 plus 3.5 would be 5.5. 2 plus 3.5 is 5.5. Now 5.5 times 2. 11. We're on a good road here. Now if you can't do these using mental math, that's absolutely no problem whatsoever. Just use some of the side margin or take out some scrap paper and work it out. But I do want you to practice these. All I'm doing is substituting the values. This is the given value and I'm substituting it. So one more time. X is going to be worth 4, which means if I rewrite this, it's going to be 6 times 4 plus 9 over 3 plus 4. And then I just work it out using order of operations. Just like if I did the other one, which is 2 times 4 plus 3.5. So it's just a substitution to evaluate. So 6 times 4 is 24. 24 plus 9 is 33. 33 divided by 3 is 11. 11 plus 4, the whole thing should come out to be 15. Now I'm going to do 4 plus 3.5 is 7.5 times 2. 7.5 times 2, also 15. So I can fill it on my table. So according to the table, these expressions are equivalent. Let's try to graph it. You might be wondering, I have no idea how to graph it. I don't expect you to yet. We know that x is going to be worth 0 or 2 or 4. So if I were to make 3 ordered pairs, remember an ordered pair is x comma y, I'd have an ordered pair that started with a 0. I'd have an ordered pair that started with a 2. I'm pulling these right off the table. I'd have an ordered pair starting with a 4. So how do I know my y value? My y value would be the next number, the one I got after I plugged it into the expression. So this is my input, this is my output. So 0 gets you 7. 2 in gets you 11 on the output. 4 on the input gets you 15 on the output. Let's do this here. 0, 2, and 4. For the next expression, 0, 2, and 4. If you put 0 in, you get 7 out. If you put 2 into this expression, you get 11 out. If you put 4 into this expression, you get 15 out. If you notice, these ordered pairs are a match, which means if we graph them, they should be exactly the same line. So if x is 0 and y is 7, the first dot is approximately here. That's about 0, 7. The next one is x is 2 and y is 11, which is right about here. So you go over 2 and up 11. 2 and 11. The next one is 4 and 15. You go over 4 and up 15. You can see, even though I'm just sketching it, it's making a pretty decent line. And it would continue to do so if we continued to put in new values for x and test it. Now, I could graph this second group of ordered pairs, but because they're a match, the graphs are going to overlap. When the graphs overlap, the expressions are equivalent. When the graphs overlap, the expressions are equivalent. All right, so now you've seen table, graph, and the last thing we're going to do is a property proof. And that may not be the official name, but what I'm trying to get at is I'm going to simplify each expression. And then as I simplify each expression, I'm going to tell you which property allowed me to do that step. And hopefully in the end, we'll get two equivalent expressions that have simplified to the exact same thing. That's what we're hoping for. All right, let me get situated here. We're going to want to take a really good look at this. Now, I haven't worked these out, so we're going to work it out together. I'm going to check the answer key at the end and make sure we're right. I'm going to start with this one because he's trickier. We tried some of this on the warm-up. It's the warm-up with the MP3 player and the songs, and we were trying to figure out Marilyn and Cody's expressions, and we really struggled with this. With this, you can use the distributive property, which means this whole element here, this term, can break up, where it can be 6 over x, because that's not right. Do over. Do over. Take out the white out. Now that's starting to feel like real life with us in the classroom. 6x over 3, rather. That's what I meant to do. Plus, who else over 3? What's the other part? 9 over 3. Plus, you cannot leave out the 4. It doesn't just disappear. So the property I did for this line was the distributive property. That's what's happening from here to here. Now we need to determine what's going to happen next. What my gut tells me to do is work out the division. So I'm curious what the answer key is going to tell me to do. It's not even that fancy, but there is division here. So I think it's fair to say that we need to identify the operation that we're about to do. Because 6x divided by 3 would be 2x. 9 divided by 3 would be 3. The 4 doesn't go anywhere. So from here and here to here to here, we did an operation, we did division. Now, I want to group. like terms together. So I'm going to do this. You could obviously use the chart because that's how you combine like terms. That is the tool I have given you to help assist you with that process. But here I am applying the associative property of addition, associative, because I want to group the constants together. And by doing so, if I apply the order of operations, I am forced to add the 4 and the 3 together first. So then I'm going to get 2x plus 7. All I've done there is addition. Okay, taking a little glance at the answer key to make sure it agrees with me, and yes, perfection. Now we're going to try the other side. This was expression number 1, here's expression number 2. We're thinking if they're equivalent, like we proved with the table and graph, that the expression should come out to this. So let's see what happens. Now I'm looking at this, and I hope you're noticing now that a certain something is happening here with these parentheses. Something you can use the area model with? If you said distributive property, you are correct. So I'm going to do 2 times x and get 2x plus 2 times 3.5. 7. That's it. Distributive property. Looks like I'm done. There's nothing else to do. This one was way easier. So, distributive property, we simplified to 2x plus 7. Several properties got us there, but it's also 2x plus 7. We have used properties here and here, and operations here and here to prove that simplifying both expressions will lead to the same equivalent simplified expression. So I hope some of this cleared up any misconceptions or concerns you had during class today and during our warm-up. This page should be really helpful in the future because now you know 3 different strategies in which to prove whether they are equivalent. Thanks for joining me. I'll be back momentarily with the remaining pages.